Just notifying everyone that the session is being recorded. I'd like to welcome all the speakers today. We have engineers from Cadence, Paul and John, and welcome to you all. So this is the CMC hosted webinar, and the goal is to talk more about Cadence Multichip Design Platform, chiplet-based RF system design. So by way of introducing why we are running this webinar, I wanted to talk about our Basecamp program. And this is with the idea that everyone is equipped with both the CAD tool aspects, methodology, and hands-on training, which will eventually lead to helping you make hands-on fabrication and make devices and test them. So that's the big goal behind having these Basecamp courses. Today's webinar is part of our RF Basecamp. As a precursor, we still have open self-paced learning available through our cloud interface, which is this introduction to EMX Planar 3D solver, and that uses Cadence EMX rack. So you could still register to this because it's a self-paced training. The idea of today's webinar is to present to you the other tools that are available from Cadence and various pieces that might be of interest. And we would like to hear more on what the interest from the audience today is on having a more hands-on detailed session. So we have gathered some feedback from your registration form, but we would like to hear more as you listen to the details from our Cadence engineers today. And there's more information here on each of these links, and we can share them later with the participants. So I'll now go on to introducing our presenter today. Paul is the Cadence Solutions Architect and supports custom flows for Mil-Aero customers. And prior to designing these flows, he's supported Cadence Liberate characterization tools and specialized in the development and deployment of Liberate AMS. And he has got the experience of 20 years in mixed signal design in RF and data conversion, SerDes, and photonics. And he holds 15 patents in these areas. He's based in Pennsylvania and has been with Cadence for 7 years. We also have John Bennett. So if you've met or interacted with John in our previous sessions, he has also helped put this all together, and we will be working with him in putting together the more hands-on training session. So welcome, John and Paul, and I'll turn it over to you, Paul, so you can start with the presentation.
Thanks for the great introduction. As Gayarthi said, I'm Paul Mosinskis. I'm a Solutions Architect with Cadence, and today we're going to be talking about our multi-chip design platform for chiplet-based RF designs. So what is the Virtuoso Design Platform? Well, the Virtuoso Design Platform is really a cross-platform chip package co-design and co-analysis solution that integrates a bunch of our tools together. So it integrates Allegro, Virtuoso, Clarity, EMX, and Celsius, which is our thermal solver, together in one sort of cohesive environment. It lets you go from multi-chiplet layout to package layout to EM and thermal modeling, and then move backwards from, say, EM modeling back to your IC layout and back annotate those the EM extracted parameters. And so today we'll be talking about all these tools, how they work together, and how you might take advantage of them. So what's the advantage of using a cohesive flow like this? One of the big advantages is that we have a single source system level database. So we're storing the data in Virtuoso and the Virtuoso-like database, which allows us to move both packaging, packaging and IC data back and forth between those two realms without having a bunch of separate, disparate files. And that has some real advantages. So one of those being that you don't have a lot of little files sitting around. Those files can get out of sync, and those out of sync files can ultimately generate errors in tape outs or analyses. So the main packaging tool that Cadence uses is called Allegro Package Designer, and this is an industry-leading tool that's used by a number of companies, over 400 companies worldwide. It can be either schematic or table-driven, connectivity on the fly. It can be partsless, can be directly edited from layout. There's over 500 user-definable rules for checking the design as you're drawing it. And it can produce, critically, it can produce the PCB and IC manufacturing output. So not only can it produce GDS2, but it can produce Gerber data, which is the standard for making packages and boards. Allegro Package Designer can go from things that are very simple, like lead frame designs, all the way up to things that are very complicated, like fan-out designs. And everything in between. And so this is not just a point tool. This is a tool that can grow from something simple to something much more complicated, depending on what you're interested in. So we have people doing, BGAs in the design. We have people doing chip scale packages in the design. We have people doing RF modules in this tool, and everything kind of in between. So a little bit about Virtuoso Package Design. Virtuoso Package Design supports this edit in concert capability. And this is a real advantage for those who are actually co-designing their IC and package at the same time. So using Virtuoso RF's edit in concert capability, you can actually dynamically switch between the die view and the package view on the fly. So you can dive down into your die view and then switch back to your package view on the fly. And this has some real advantages for 3D IC extraction. So when your electromagnetics begin to dominate, one of the major advantages of this edit in concert technology is you can actually use it to select metallization on the IC to be included in the 3D EM package extraction. Pretty much every other solution that's out there requires you to manually crop that out, drop that in, or draw that in to your 3D simulation, whereas our solution can manually extract the metallization from the IC and put it in the simulation automatically. Now, that's not a capability that would be very useful without a high-performance 3D simulator, so we're going to talk about that in a few slides, and that's going to be our Clarity simulator. So what are the benefits of Allegro APD and Virtuoso RF? Well, a single database means data management and translation are all automated. This IC metallization can be automatically extracted. Like I mentioned, all piece parts come from the same database. Really, what this means is the chances of error are hugely reduced, and the time savings are significant. So what does that mean? It means you can run more experiments, you can run more trials, you can just do things in a faster way. We also support automatic stitching of parasitic insertion, which means there's less error prone. Your work is less error prone because you're not trying to manually insert these parasitics. And ultimately, you're free to run more what-if experiments and increase the likelihood that your design is going to work the first time because you've been able to run these experiments. So in this flow, we offer a number of different extraction solutions depending on what level, complexity, and frequency you're working at. Starting from the bottom here, if you're extracting the entire IC and you need the entire IC, we offer Quantus RLC extraction. If you need precise inductor, planar inductor extraction, we offer EMX, our planar method of moment solver, and that works really well. You guys have had some experience with that. And then as you move to more complex three-dimensional shapes, we have Clarity, which is our true 3D FEM solver, and that is really good for things that are complicated, things where the 3D shape matters, like bond wires or packages where the size of the third dimension is significant compared to the XY dimensions. So what is EMX? EMX is our planar electromagnetic solver. It's a large-scale, full-wave planar electromagnetic simulator. It's able to simulate full component assemblies with all the coupling to avoid various sources of error. It's very easy to use. It's actually integrated into our Virtuoso suite, and it basically allows you to go mask layout to S parameters with a few clicks. Now, for more complicated problems or problems that are operating at higher frequencies, we have Clarity. Clarity is our full 3D FEM solver. So this is for problems where you need that full third dimension. You need to understand what's happening at very high frequencies, or you need to understand what's happening in the Z dimension, as I mentioned, say for a bond wire. So Clarity supports things like smart meshing, where you have a dense mesh and high field regions and a coarse mesh and low field regions. It supports hundreds of ports and hundreds of CPUs. Really, Clarity has some pretty breakthrough technology, which allows the problem to be split across hundreds of CPUs in a way to where not one machine has a very large memory requirement. It supports cross-fabric port identification. That's the feature I was mentioning earlier, where you can click on metallization in the IC and have that included in your 3D EM simulation directly. It supports heterogeneous material support directly from the underlying technology files. And what that really means is I can have a SIGI design, I can have a CMOS design on the same package, and I can actually extract those in Clarity at the same time if I want to. It supports an explicit DC solution, which is really critical for making good S parameter files. Anybody who's worked with S parameter files knows that that without a DC solution, S parameter files have trouble converging. And it's integrated in the Cadence Virtuoso environment, so it makes it very easy to get these results. There's not a lot of learning to actually get a high quality 3D EM solution. Finally, there's Celsius, which is our thermal solver. Celsius can work at multiple levels, be that chip, package, or board. In your chip, you might want to understand where you have thermal hotspots. At the package level, there's a similar desire to understand how the heat is spreading. Perhaps at the board level, you're trying to understand how to dissipate the heat that you've generated in your package across various surfaces. And Celsius can work at all those different levels. Celsius uses the same computation engine that Clarity does, so it can also be distributed across hundreds of CPUs to solve very complicated problems. So having talked a little bit about the tools, let's talk about what we see as a typical RF design flow and how the flow that we propose can help solve this issue. So the typical RF design flow starts out with a system concept, some idea in somebody's head about what an RF design would be like. Then we see people doing system simulations or lineup simulations in spreadsheets still today. Laminate design is done in primarily microwave tools like ADS or AWR. EM extraction is done in HFSS, and then simulation is done in either AWR or ADS. Now, there's a couple critical things to note in this flow. The first thing is that while laminate design, it could be done in ADS, the simulation for that laminate might be done in AWR. So there's really very little connection between the design and the simulation. So if you lay out your tool and if you lay out your design in one tool and you extract it or simulate it in another tool, then you can end up with a pretty big difference between what you're actually taping out and what you actually simulated. Additionally, LVS is usually done with a standalone schematic. This case, it's listed as ADS, but it could be an AWR schematic. That standalone schematic is not simulated, and so LVS really just validates that there's a schematic that matches the layout design, but it doesn't validate that the simulation matches actually what's going out to manufacturing. And so the combination of all these factors really limits this flow to making sure that you can get your design right. And I guess finally, in a general sense, most of these point microwave tools, which is what we consider ADS and AWR, they limit the ability to include silicon die. And so while they excel at RF solutions, if you want to throw 10,000 CMOS transistors into the simulation, the electrical simulation, there's a sort of a capacity limitation. So what kind of solution are we proposing? Well, we're proposing a solution where we use our system simulation tool, VSS, to do system exploration. That's things like link budget, spur analysis, antenna radiation patterns. These all can be explored using VSS very rapidly. It's an ultra high capacity system simulator. So you can, do constellation mapping. You can look at all sorts of power output levels, and you can look at those in almost real time. So it's very easy to explore how your system might perform. And then moving from VSS, we move to implementation, where the module schematic is done in Virtuoso and the laminate design is done in a combination of APD and VRF, and data is seamlessly moved back and forth between these two. Now, having one database where you're basically implementing and laying out your design has some real advantages. One being that you're doing your functional verification, your performance verification, and your DRC and LVS all on the same database. So whichever you've simulated is actually what you're going to tape out. Finally, that same database can drive both EM simulation and thermal and mechanical simulation from the same database. And so, again, there's not a translational issue, and there's no set of third-party database. Excuse me, there's no set of additional databases there. And so in our flow, we end up with one common layout and schematic for all analysis verification and co-simulation for all types of die in a single flow. And when we say all types of die, we really mean types 3, 4, and 5. So we'll talk a little bit more about that as a feature of Spectre that's going to be coming out in the near future. So it's a great flow. We've described it, but really, can we do anything with this flow? So to sort of flesh out the flow and provide an example of what we could do with the flow, we built a sample design in our flow to test it. And the sample design included a CMOS baseband chiplet, 2 SiGe PA chiplets, and a bipolar regulator. So really stressing the heterogeneous nature of the design. We included transistors in the baseband chiplet. We included some Verilog A in the chiplet. We extracted part of the chiplet using EMX. We extracted the interconnect using Clarity. We have both SiGe, CMOS, and bipolar technologies, all on a single organic laminate design. And that organic laminate design in cross-section looks something like this. We have 2 8-bit channels coming into a baseband chiplet, which is mounted to the bottom of a laminate BGA. From that baseband chiplet, we have 2 RF signals which come up to our power amplifiers, and then those power amplifiers go out to antennas. In the background here is our regulator, which is not shown in this cross-section, but is a little bit easier to see on the layout views, which are on the next few slides. So what does that look like from a schematic perspective? Well, from a schematic perspective, we have our baseband chiplet here. We have 2 power amplifiers here. We have our regulator here, and then we have all of our routing extracted in full FEM 3D from Clarity. Note that the baseband chiplet routes are fully extracted because they're running at a frequency of 1 gigahertz. Additionally, the routes around the PA are also extracted, and they're extracted together. Both the input and output routes are extracted in a single Clarity model, so that crosstalk can be studied between the input and the output of the PA. What does this look like from a 2D view? Basically, we have our one PA sitting here and on our layout, a second PA sitting here on our layout. And finally, we have our baseband chiplet sitting on the bottom, shown in red, and our regulator chiplet sitting on top, shown in purple. Now, it's a little difficult to see this in 2D, but if we switch to 3D, it's a little easier to see the locations of the various dies. So the PAs sit here on the top of the organic laminate, along with the regulator, and the baseband chiplet sits on the bottom of the organic laminate in the die up position. So the flow that we're proposing, one of the key aspects of it is being able to simulate the whole thing together. And so Spectre, our simulator, which is known for CMOS performance, has been extended to be able to handle multiple technologies at the same time. So a typical RF lineup might include silicon, GaN gas, and SiGe for various parts of the design with clarity back annotation. And Spectre can handle this simulation entirely end-to-end, whether that be frequency input to frequency output or time domain input to time domain output. You can simulate the whole thing together in Spectre end-to-end, and this provides some real value for validating your system, not in pieces, but in whole. So you can understand the nonlinear effects of all the blocks. You can do time domain simulation of all the blocks. And you can actually, in the very near future, we'll be able to support 3.5 models in actually Spectre. So we'll be able to co-simulate your silicon, your SiGe, your SOI with, say, your GaN gas devices directly. Critically, once you're done with that simulation, you can use the same netlist that you use for simulation for validation against your physical design, and therefore you know what you're taping out is what you simulated, and you're going to get something that works. So does it work? The answer is yes, the flow does work, and it actually does produce results. So we took our little example design and we actually put some digital data into it and upconverted it to 2.45 gigahertz. So on the top, you'll see this red line, which is the analog representation of a digital sine wave that's going into the DDR port on the design. That analog sine wave has been upconverted to 2.45 gigahertz. Likewise, on the second channel, we're converted a slightly different frequency analog sine wave. That's also been upconverted at 2.45 gigahertz. So we have successful AM modulation through the entire system, co-simulating, in this case, a CMOS, a SiGe, and a bipolar die together. And the sim time for this time domain simulation is approximately 55 minutes using 8 threads. Likewise, we were able to do a large signal frequency domain simulation or harmonic balance simulation to look at both return loss and crosstalk, and found an interesting finding. For the output of the power amplifiers, the return loss is approximately the same, about 6 dB, looking back into the power amplifier ports. But if we start looking at the crosstalk, we notice that the crosstalk from B to A is different than the crosstalk from A to B. And this is what we would consider a good finding. Primarily because there's a difference between the crosstalks, but the routing, if we were to look at it, would be the same. So this is an opportunity to either improve the crosstalk or understand why the performance of one is better than the other in what appears to be nearly identical layout. Finally, we ran a thermal simulation of the entire design. So here we have our 2 power amplifiers, power amplifier A and power amplifier B, along with our regulator. You can see the regulator gets to be the hottest at 87.5 degrees, with the power amplifiers nominally following along. The baseband chiplet is on the bottom, but its power dissipation, being that it's in CMOS, is negligible compared to the heat generated by the regulator and the power amplifier. So, in conclusion, we can use the Virtuoso System Design Platform to both build and test complex RF systems. We have support for both simple and complicated package technologies. We have integrated we've integrated multiple electromagnetic solutions. We can use both low-level like models like transistors and behavioral models like Verilog A in the same simulation. We're running all from a common database, and we can understand thermal impacts on that database. And for those of you designing in 3.5 technologies, we have support for 3.5 models coming very soon in Spectre. And that concludes our presentation.
Maybe then I'll quickly segue into a few other offerings that we have. I wanted to quickly mention that we have a program called VIE. It's a virtual incubator environment supporting startups. So we have a bunch of CAD tools that we support, and we also provide access to fabrication through multi-project wafer runs or dedicated runs when the scale-up happens. So if that's of interest to anyone, we are happy to have provide more information or have a chat if you'd like. And we do have an events calendar. I just posted a snapshot of the few events that are coming up in February, but you can have a look at the events we have planned out for the entire year. And part of these, sometime during the year, we would like to have a more hands-on session with what Paul has described today. So we look forward to your feedback, and also want to thank everyone who's provided their feedback at the time of registration. Okay, I think with that, I'd like to thank Paul and John again. Thank you for this presentation, and we really appreciate your time.